This is my homebrew 8-bit CPU, and in the previous episode I've added this handy little display that now allows me to write programs that write messages to the display. This is the current test program that we have. It sends a bunch of commands to the LCD, and after each LCD write there are a few knobs that make the CPU wait until the LCD is ready to accept the next command. It would be nice if we didn't have to add these knobs though, so let's just try removing them, and then recompile the program and write it to the flash memory. If I run the program, you can see that the display starts to be configured, the bars disappear, but then nothing happens, the configuration never finishes. And that's because the CPU is writing to the display faster than the LCD can handle. When we still had the knobs in the program, the CPU would issue a new write to the LCD, but then insert knobs and other instructions and basically wait until the LCD was done, and only then would the CPU issue the next command write. However, when we remove those knobs, the CPU would write to the display would become busy for a few cycles, but then since the CPU doesn't artificially slow down, it would issue the next write way too early while the LCD is still busy, and the LCD would just not see that write, it would just ignore it. And so all these writes that happen while the LCD is busy would just fall through the cracks and never be considered, and it's only the writes that the CPU issues while the LCD is idle that will go through. Let's take a closer look at what's going on. The problem is that the CPU sets the enable line while the LCD circuitry is still busy. Let me add a yellow LED between that enable line and the busy line, such that it lights up whenever we're trying to enable the circuit while it's still busy. Now let's step through the program and see what happens. So we've cleared the register file, and we've cleared the flags, and now we're loading the first LCD command into register R0, which we're then using for an LCD command write. And as you can see, the enable light goes on of the LCD, but the LCD is not busy at the moment, so all is well. This puts the LCD circuitry into the busy state, and we're loading the next LCD command into register R0. This is a clear display command, and now we're at the next LCD command write. And this one is problematic, this one is too fast. The LCD is still busy, but the CPU already sets the enable line. And correspondingly, this new yellow LED goes on to indicate that we're trying to talk to the LCD too quickly. To fix this issue, we need a way to stall the CPU and prevent it from making any progress in the program if the stall condition here happens if we're trying to access the LCD too quickly. And if you recall from one of the very first few episodes when we built the program counter, the program counter actually has an enable input that allows us to halt it and freeze it in place. And we can use exactly this enable signal here. Let me try this by hand first. We have the enable signal down here, and this is active low, so if I set this low, nothing happens and the program counter is enabled. But now since we're trying to access the LCD too quickly, let me disable the program counter. You can see the enable LED goes off. And when I now toggle the clock, the CPU stays put in its current location in the program, but the LCD is able to finish its transaction. So the display cleared, the stall condition here disappeared, we're no longer trying to access the LCD while it's busy, and we're still at the same position in the program, still at this point where we're trying to send the next command. So since we no longer have to stall, I can enable the program counter again, which then starts the next transaction at the LCD, preloads the next command, and now we're in the same situation again where we're trying to access the LCD too quickly while the LCD is still busy. And when I now stall the program counter again and toggle the clock, the clear display command goes through properly, and I can re-enable the program counter, do this once again for the next command, which is going to turn on the cursor. Pretty neat. So by manually disabling the program counter in response to the stall condition, we were able to get the old behavior of the program back where we actually reset and configure the display properly. I think all we have to do is connect the stall condition of the LCD control circuit to the program counter enable line, such that when we have a stall detected here where we can make forward progress, we provide backpressure into the CPU and prevent it from making progress until the stall condition clears out. And this is a very common scheme in digital electronics. We have a decoder here which picks one of the functional units. It does this with a 2 to 4 line decoder. This is taking a 2-bit number, the functional unit ID, and then it has 4 output lines, and it's going to pull one of the lines low to enable it. In digital hardware design, that's usually called a valid signal because you're presenting a unit with some valid input, And what's commonly done is to have the unit respond with a ready signal, where the unit can indicate whether it's actually ready to accept that valid input that you're presenting, and it can make forward progress. And in a sense, that yellow LED here is the inverse of a ready signal. It basically indicates back to the decoder that the unit is not ready to make forward progress. So in addition of picking one of the functional units in the decoder and setting its valid input, its enable line, we also want to have a corresponding multiplexer, which takes the ready response line from that functional unit, selects it, and then uses this to stall the processor. And so when we're selecting the LCD, and the LCD isn't ready, we're going to stall. But other units can do the same thing. If we have a load store unit which accesses memory, we can enable that unit, and if that unit isn't ready to make progress, it can respond with its own ready signal to indicate that it has to stall, and the CPU will then do the right thing. This 224 demultiplexer which we're using has a corresponding 4-input multiplexer, the 74HC153, which we've used in other places in the CPU, and I'm going to use that here as well. This has 2 enable inputs, which we're going to pull low to constantly enable the multiplexer. And we have 2 select input lines, which are basically the 2-bit binary number, which indicates which input we want to select. I'm going to connect this to the functional unit ID that we're also using for the demultiplexer to enable the units. And then we have 4 inputs on either side plus 1 output that produces the selected input signal. The output of this multiplexer we want to use as the enable signal of the program counter. And the 4 corresponding inputs we can connect to whatever ready signal that we get from the different functional units to provide back pressure. The move unit, the ALU, and the branch unit don't provide any back pressure. They're always ready to make progress. So let me connect the inputs that correspond to those units to ground to constantly enable the program counter, which has an active low enable. And the input for functional unit 3, which is the LCD unit, we can connect to the busy signal of the LCD unit. So whenever the LCD is busy and that busy signal is high, we're going to select that as the enable for the program counter, and because the enable is active low, that will cause the program counter to stall. In theory, that's all we need. Let's take a look at the program again. Nothing catches fire, that's a good sign. Let me skip the register clearing. Now we're loading the function set command into register R0, and then we're doing an LCD command write. And indeed, there's the LCD command write enabling the LCD unit, but because the LCD unit is not busy, the program counter stays enabled. Now the LCD is busy, we're loading the next command into register R0, and now we're trying to do another LCD command write. This is a clear display command, but now the LCD unit is busy and not ready to accept our command. And correspondingly, the new multiplexer here picks this busy signal, this back pressure signal, and feeds it into the program counter, and the program counter is now disabled. And when I now toggle the clock, the LCD unit goes through its motions, but the program counter stays stalled and stays still until the LCD is able to accept this new instruction. Now the LCD is done, no longer busy, so the stall condition is gone, and the program counter is enabled again. Pretty cool, that seems to be working. So now the program works without any knob commands in there to artificially slow down the processor. So this concept of handshaking with a valid and a ready signal, where we try to present new data with a valid signal, and then we have a unit presenting a ready back pressure signal indicating whether it can process what we're presenting, that is a very common pattern in digital hardware design. And apparently, this small CPU can do that as well. And I have a feeling that this will become a very common pattern in this build. Now, it would be cool if we could also read from the LCD. That would allow us to get the current position on screen and read the busy flag for some of the commands that take very long. This is how the current write access looks like. We pull the RW line low to indicate a write, and we set the data that we want to write to the display from the CPU. To do a read, all we have to do is change the RW line to a 1 to indicate a read, and then instead of having the CPU drive data onto the data lines, we wait for the LCD to do so. And the LCD will generally do so after the E signal goes high. There's a little bit of a propagation delay. But generally speaking, we can assume that in the last cycle of this transaction, the read data is valid and we can do something with it. And then all we have to do is stall the CPU in all but the last cycles to make it wait until the read data becomes available. To implement this, we first need to make sure that we can drive the read data coming from the display onto the right data bus such that we can store it in the registers. I'm going to use a 74HC541 buffer chip between the LCD data and the right data bus. The input side of the buffer we're going to connect to the data bus coming from the LCD. And then we need to decide when to enable this buffer. In the other functional units we have, especially the move buffer and the ALU, we're using the enable signal coming from the decoder to enable the output and allow those units to drive their result onto the right data bus. And I'm going to do the same thing here. Whenever the LCD unit is enabled, we're also going to enable its output buffer such that whatever the LCD produces gets pushed on the right data bus. And the decoder can then decide whether to write this back into the register file or not by setting the write enable on the register file. We already have this enable line here coming from the decoder, so I'm just going to forward that to the output buffer as well. And the second output enable of the buffer I'm just going to tie low because we're not using it. And then last but not least, I'm going to connect the output of this buffer to the right data bus, such that whenever the buffer is enabled, we're driving the LCD data onto the right data bus. That deals with the data movement, but we now also need to make the CPU wait for the read data to become available. Right now, the ready signal returning from the LCD unit to the decoder is connected directly to the busy signal of the unit. That works for writes because it only stalls the CPU when it tries to access the unit while it's busy. But for reads, we want to always stall the CPU until the last cycle of the read where data then becomes available. Conveniently, the 74HC163 counter chip that we're using in the LCD unit has a carry output, which is high on the very last count of the cycle. So this is exactly the signal we want. The result data is valid if we're reading, if the RW signal is high, and if we're in this final cycle, if this ripple carry output of the counter is high. I'm going to use a green LED to display this result valid signal. Then I'm going to use one of the NAND gates we still have available. The RW signal, which indicates whether we're reading or writing, is going to come from the latch we have where we store the RS and RW signals. The other input of the NAND gate I'm going to connect to the ripple carry out of the counter, the signal that indicates whether we're in the last cycle. And the output of that NAND gate is going to be our result valid signal. So now we have two ready signals that the LCD unit generates. We have the busy signal, which is our ready signal for writes. And we have this new result valid signal here, which is our ready for reads. All we have to do at this point is pick between the two, depending on whether the decoder wants to read or write, and return that signal to the decoder as our ready signal from the LCD unit. I'm going to use a 74HC157 chip. This chip has a bunch of 2-input multiplexers, which is pretty convenient for this. And I'm just going to place it on this small breadboard we have here, because I think this is going to be temporary. In the future, when we look at autonomous write back of the units, we'll probably need to rewire this a little bit. But this will do for now. I'm going to tie the active low enable of the multiplexer low, such that it's permanently enabled. The select line of the multiplexer I'm going to connect to this read-write line coming from the decoder. This is what indicates whether we want to do a read or a write, and we can use that to pick the correct ready signal. Input 0, which corresponds to a write, we're going to connect to the busy signal, which we've been using up until now. And then we're going to use the output of the multiplexer as the ready signal we return to the decoder. You can also shorten the wire a bit. And input number 1, which corresponds to a read, I'm going to connect to this new result valid signal. And that's about all we need to change on the breadboard. Now in theory, the program should still work as before. Pretty nice, looks like we didn't break anything, the writes still work. Now let's go and see if we can read from the LCD. First, let me define new LCD read instructions. We're going to have an LCD command read and an LCD data read. These just write into the RD register whatever comes back from the display. And this will have the function 3 field set to the values 2 and 3. This is pretty convenient because the lowest bit we have connected to the RS input of the display, which chooses between a command or a data access. And the next bit we have connected to the RW port of the display, which decides whether it's a read or a write. So we can just pass these bits through to the display as we've done on the breadboard. Then let's implement these in the decoder. These work almost the same way as the write instructions to the LCD. The only difference is that we set the RD mode to write only instead of read only, because we take the response, the result we get from the LCD, and we just write it into the RD register. Let me regenerate the decoder ROMs and then flash the new data onto them. And then let's add support for these instructions to the assembler. First, let me add the use of them to the test program. This fails as expected, so let's go add opcodes for the new instructions. Then let's teach the assembler how to parse these instructions. They work exactly the same way as the write instructions. We also want to display them back to the user. And the assembler needs to be able to encode them into actual instruction bits. And the only thing that changed is that the function 3 field is set to the values 2 and 3 for the command and data read, instead of 0 and 1 for the command and data write. And this works. The instructions get parsed, encoded, and then displayed back to the user. And then let's use these instructions in the LCD test program. We still want to clear the registers, initialize the display, and write the hello message. But then instead of going to the second line and writing the digits 0 through 9 onto the second line, let's read the current position on the display, add 2 to that, and set that as the new position on the display. So first, let's do a command read. This will return us the busy flag in the topmost bit, and then all the other bits correspond to the display RAM address. We'll ignore the busy flag for now. This is not going to be set at the moment because our CPU runs at a very slow pace. So we can just increment this address by the value 2, which effectively moves the cursor forward by 2. And to turn this address into a set display data RAM address command that the display understands, we have to set the topmost bit to A1. And we can use an OR with immediate instruction for this. And then we can write the value in R2 as a command to the display. This uses a command read on the display. Let's also try a data read, which basically allows us to read back the contents of the display. And I think what we could do is we could jump to the location of the E in the hello string, read that into a register, mess with the value a bit, and write it back onto the display. And in doing so, changing the E to a different letter. First, we need to jump to the position of the E. The E is the second character on the display. This is address 1. And if we now do a data read from the display, we should read back the ASCII value of that letter E at that position. This will also move the cursor from the E to the next character, so we'll want to reposition our cursor on the E such that we can replace it later. And now let's add the number 16 to the ASCII value of the letter E, which is going to translate the letter E to the letter U. And then we can do a data write to write this updated letter back to the display. And with a bit of luck, this is going to translate the hello into a proper Scott Manley greeting. Let me compile this program and then write the binary to the program memory. And then let me run the program until the hello message is printed. At this point, we've sent the last letter, the O, off to the LCD unit. The LCD unit is busy writing that. And we're now already entering the loop where we're going to write the digits 0 through 9 to the display. And so we've already prepared register R0 with the value 48, which is the ASCII code for the digit 0. Now we're going to load 10 into register R1. At this point in the loop, we're trying to read back the position on the screen from the display into register R2, increment it a little bit, and then write it back to the display such that the cursor jumps ahead. Since this is an LCD command read, we're selecting the destination register R2 for writing, and we're not using the destination register as an input operand for the operation. And this is the exact opposite of the LCD command writes we had before. So the decoder is selecting the LCD unit. You can see that the enable signal goes high, the green LED is on, but the unit is also busy, so the orange ready LED, the stall LED, basically goes on, indicating that the LCD unit isn't ready to make progress yet. And so correspondingly, the enable signal on the program counter is low, so we're basically stalling the CPU while the LCD is busy. So let's move ahead until the LCD is done writing the O. The O appears on the LCD, and the unit is no longer busy. And as an interesting side effect, we've written whatever was on the data bus of the LCD, which is actually the letter O that we're writing. We've written that into register R2 temporarily, because this is continuously enabled and is accepting data, even though the unit isn't done yet. But that doesn't matter. We'll just fill this register continuously with whatever comes from the LCD, And then once this is done, the thing that will remain in the register at the end is the data that we were interested in. So the unit is no longer busy and the orange stall LED has turned off. So the unit is ready to accept this command read that we have prepared here. But notice that the program counter is still disabled, the CPU is still stalled. This is different from the command writes. When the unit was able to accept the write, we could just let the CPU run ahead and do its thing. But since we're doing a read now, the CPU has to stall until the read data is available, until it can make progress. And this is using this multiplexer here. Because we're doing a read, we're not selecting the busy flag as a ready signal feeding back into the decoder, which causes the processor to stall. But instead, we're using the result valid signal, which indicates if there's valid read data available, and we're using that to stall the CPU. And so when I hit the clock, the unit goes into the busy state and starts to read from the LCD, and the CPU is stalled during all of that time. And then we'll reach the point where we're in the last cycle of the access, and the ripple carry output of the counter that we're using goes high, which we've used as an indicator that the result is now valid. And correspondingly, the result valid green LED goes on because we're in the last cycle of a read. And you can see that the program counter is enabled, so the CPU is no longer stalled, it's able to make progress. And over here in register R2, you can see that it was set to the value 5, which is indeed the address of the cursor on the display. We are on position 5 on the display. And in fact, this is set to 5 here already because we are single stepping the CPU, so we're really slow in comparison to what the LCD can maximally support. So even though we're only now entering the last cycle of the transaction, and only now the read data really needs to be available, it was already available in the earlier cycle, so it's already in register R2. But when I hit the clock now, this is actually the point in time where we would write the result from the LCD into the register, and it's the latest point that the LCD needs to provide that data. And it won't be until we hit like 1, 2, 4 megahertz of execution speed where this will start to matter. So when I hit the clock now, the unit goes into its idle state, it's no longer busy, and register R2 is set to the value 5, which is exactly what we expected to read back from the display. So all of these shenanigans we played over here with the multiplexer and coming up with a result valid signal seem to work, and we're able to read back at least the display address into a register. And we were able to do this completely without any knobs in the program, just by using this ready signal to provide back pressure and to stall the CPU until the data that the CPU is interested in actually becomes available. So now we're adding the value 2 to register R2. This is turning it into a 7, which is going to be our new position on the display. And then we're setting the top bit to turn this into a set display data RAM address command. And then we're sending this off as a command to the display. And when I step through the cycles of this transaction, you can see that the cursor at the end of it will jump forward by 2. There we go. Pretty sweet. All right, let me let the program do its thing. And let me interrupt it just before we mess around with the E letter in hello. Okay, at this point, the write of the final digit 9 is still ongoing in the LCD unit over here, but the program has already exited out of the loop and is now getting ready to modify the letter E. So first, we're going to position the cursor on the letter E. This loads the command into register R0 and then sends that command off to the LCD to be executed. And immediately after that write, there's a LCD data read because we're trying to read back whatever is at the cursor address. But because the previous command hasn't fully executed yet, the cursor hasn't jumped there yet, the LCD unit is still busy, we're actually holding the program here, the CPU is stalled, and we're waiting for the previous command on the LCD to fully execute, and only then will the LCD unit start to read back the data on the display there. Alright, so we've jumped to the position of the letter E, and now we can actually start executing this display data read. As you can see, the LCD unit is selected here. And when I hit the clock, it goes into its busy state, and as you can see, the RS and the RW control signals are both high, so we're doing a data read in this case, which we haven't done before in the past. And when I step through this read operation, you can see that the ASCII value for the letter E has appeared in register R1. Now we're going to send off the command to reposition the cursor on the letter E. And now we're adding the value 16 to the ASCII code of the E in register R1. And this is going to change it into a U. And then we're doing another LCD data write, basically writing this back to the display. But again, there's currently an operation in progress in the LCD unit. The cursor hasn't jumped back to the letter E. So the CPU is stalled and is waiting for this to complete. All right, the cursor has jumped back to the letter E, and now we're doing the data write of the updated ASCII code. Pretty nice, this worked like a charm. The hello got turned into a hollow, so it looks like the reads and all this backpressure logic that we've added is working as expected. It's pretty cool, and we can make use of it in a very simple program. Now, having small test messages on the display is pretty cool, but I think I want to do something a bit more fancy. Let's see if we can write a Fibonacci sequence generator that outputs to the display and writes the sequence onto the display. Let me copy the existing LCD test program. We'll keep the register clearing and the display initialization. And then instead of just writing hello, let's write Fibonacci sequence onto the first line of the LCD. This is pretty annoying to do at the moment. I can't wait to finally have some memory access in the system such that we can load these strings from the program memory directly. But yeah, at this point we've printed Fibonacci sequence to the LCD and we can start generating the numbers of the sequence. As I did before, I'm going to dedicate R1, R0 to be the lower of the two Fibonacci numbers we track, and R3, R2 the higher of the two Fibonacci numbers. And I'm going to initialize both of them to 1, and then I'm going to make register R4 be the index that we count up such that we have an index to print on the display too. I'm going to be printing number B to make sure that when the addition overflows, we have already printed the last largest number that didn't overflow. I think I'm going to set the index to 2 because the variable A contains the first Fibonacci number and the variable B contains the second Fibonacci number, and that's the one we're going to start printing with. All right, now to the fun part. I think I want to make use of this new read capability we have on the display to read the current position of the display and then jump to the next line on the display such that each number is on the next line. And then when we reach the bottom line, we're going to clear the display such that we jump back to the top of the screen. The lines have somewhat weird addresses. Lines 0 and 1 start at the nice round hexadecimal number, but then lines 2 and 3 are basically just 20 characters into those nicely aligned numbers. And this essentially makes all the even lines, line 0 and 2, start at the beginning of the display RAM, and the odd lines, line 1 and 3, start somewhere in the middle of display RAM at hex 40. And so to jump to a new line, I think we first need to read the current display address. We can do this with an LCD command read, which is going to give us the busy flag in the topmost bit, which we're going to clear, and the current address in the lower bits. So at this point, register R5 contains the current display address, and I want to load register R6 with the appropriate command for the LCD to jump to the next line. So we're going to look at the address in R5 and do a few comparisons and tests and figure out on which line exactly we are. The easiest one is to figure out if we're on odd or even lines by just checking this bit number 6, I think it is, the one that distinguishes address 0 from address hex 40, and this will tell us whether we're on line 0 or 2 or 1 or 3. And then we can build a simple if statement. If this bit is non-zero, we're on an odd line, and otherwise we're on an even line. If we're on an even line, line 0 or 2, I'm going to assume that we're on line 0 and load the command to go to line 1 into register R6. And then we're going to check R5 and see if we're actually on line 2, if we're beyond the offset 20 on this line. And if that is the case, I'm going to override the value in R6 with the command to go to line 3. And then we're going to do the exact same thing for the odd lines. The only difference in the odd line case is that if we are on line 3, which is the last line, we are going to use a clear display command to go back to line 0 and clear the entire display. And so when we reach the end if, R6 is nicely prepared with the command we want to send, so we can just do a LCD command write and execute it. So at this point, we have jumped to the beginning of the next line, and we can start printing the current Fibonacci number. First, I think we want to print the current index of the Fibonacci number. And since the CPU isn't very capable yet, I'm just going to print these numbers as hexadecimals, because then we can just print the upper 4 bits first. That's going to be the first digit, and then the lower 4 bits, that's going to be the second digit of the hexadecimal number. Printing as hexadecimal means that the numbers 0 to 9 we map to just the digits 0 to 9, but then the numbers 10 to 15 we're going to map to the letters A through F, which are at a slightly different offset. To get started, we'll extract the upper 4 bits of the index. Then I'm going to subtract 10, such that we can look at the flags and decide if we have a number below 10 or above 10. If the current digit is 10 or above, we have to add 7 to it, which is the correct shift to go from the ASCII code of the digit 0 through 9 to the ASCII code of the letter A. And if the digit is below 10, we'll just skip this step. And then we have to undo the subtract of 10 we did earlier, and we have to add the offset of the ASCII code for the digit 0. And at this point, our 5 contains the ASCII code of the digit we want to write to the display. And then we're going to do the exact same thing, but we're going to extract the lower 4 bits of the index and write that as the second digit. After we've printed the index, I think I want to print a colon and a space. And then we're going to do the exact same thing again for the upper and lower byte of the Fibonacci number. So I'm just going to copy that code and strip away the comments. And then once more for the lower 8 bits. There's a lot of repetition here. We're printing the index, and then we're basically copy-pasting that exact code to do the printing of the Fibonacci number. And usually you would put that into a separate subroutine, a function you can call that you can then return from. We can do this on the CPU as well, but we're currently a bit pressed for registers. We're already using register R5, and we have used register R6, and that's all the registers we have. Once we have memory attached to the CPU, we can have a stack, and we can use the stack to store away variables we're not using at the moment. And then we can have a proper call stack and move some of the stuff into subroutines. And we'll be doing that soon. But for now, I think this is going to be good enough. And after this piece of code here, we should have printed the index, colon, space, and then the Fibonacci number in hexadecimal. So the only thing left to do after that is to actually compute the next Fibonacci number in the sequence. I'm going to do this with a bunch of moves because the LCD code dominates the runtime anyway, and we don't really need to be very efficient here. At this point, after the add with carry, the carry flag is going to be set if the addition overflowed, and we can use that as a condition to exit out of this loop. Otherwise, if no overflow happened, we're just going to increment the index, which is in register R4, and then we're going to go back to the beginning of this loop, which was the new line label, where we jump to the next line. And then down here, after we exited the loop, I think it would be kind of cool if we printed a little bit of text to the display to indicate that this is the largest number that we could reasonably compute. So I'm just going to print the message max in parentheses after the largest number. And at this point, if all went well, the last line should read 18, colon, space, B520, and then max in parentheses. 18 is the hexadecimal version of 24, because the 24th Fibonacci number is the largest we can represent, and that's the number 46,368, which in hexadecimal is B520. And I think that's it. That's our Fibonacci program that prints to the LCD. Let me try and compile this. Pretty interesting, this is an assembler error that hasn't come up in the past. The assembler is complaining that on this jump to the new line label instruction here, the immediate value that it has to insert to realize this jump, the offset to go from this instruction back to the new line label, is minus 154, and this is actually larger than the minus 128 to 128 that it can represent in this instruction. So the loop we've written is so large that we can't branch back to the beginning of it with just an immediate jump operand. This is a common problem. One solution would be to load the absolute address of the beginning of the loop into 2 registers and then use a jump with an absolute register address. Or we can use a small trampoline, have a label in between in the loop to kind of go via that to the beginning of the loop. I think here in the middle of the printing would be a good spot for this trampoline. This effectively puts a jump instruction to the new line label somewhere in between this code, which we can target from all the way at the bottom of the loop. And if we reach this point just from the regular program flow from above, we're just gonna jump over this small little trampoline. It's pretty dumb, but can be quite handy in practice. And this now compiles. Let me write that to the program memory and then install that back in the CPU. And then let's give this a try. When I hit run, we should see the program initialize the display, write the Fibonacci sequence message, and then go about populating the display. So here we go. And that is fantastic. That works like a charm. This is the first fairly involved and complicated program running on this CPU, and it produces nice output on an LCD. The fact that we can print the Fibonacci sequence like this means that we have the ALU all up and running. We can do complicated control flow with branches and conditions that we test on the values in the registers, and that the reading and writing from and to the LCD is working together with this backpressure here, where we have to stall the CPU under certain conditions. And yeah, this prints flawlessly, and indeed, we can see that the largest Fibonacci number is hex 18, and then hex B520, which is the 24th number, 46,368, which we've seen before. With the current setting of the clock generator here, the CPU is running at roughly 100 Hz. So we're doing roughly 100 instructions per second, except for the LCD commands that can stall under certain conditions. And I can crank this up a little bit. If I turn my speed potentiometer all the way to the limit, the CPU is roughly at 2 kHz. And when I hit reset and let it run, we're going to see that the Fibonacci sequence is going to fill in much more quickly. And it's already done. Ran pretty quickly. I can also remove this one capacitor down here, which is basically throttling the free running clock here, and this is going to make it run at a fairly quick pace. This is now running at roughly 210 kHz, but when I hit reset now, you can see that the LCD basically prints garbage at this point. And I think what's happening here is that the display clear command and some of the other commands that the LCD supports take quite a while to fully execute. I think if we do a display clear on the LCD, what the internal controller module does is it writes the space character to every single location in the display RAM. So basically it goes and it overrides the entire contents of the display with just spaces. And that can be pretty slow. When we're reading from the display, when we're doing a command read, we actually get back a busy flag that we can look at to prevent this from happening. And so in the future, when we interact with the LCD, I'm pretty sure that's what we want to do before we talk to the LCD, at least after we've issued a display clear. We want to investigate the busy flag and just make the processor stop and kind of requery the busy flag and wait for the LCD to become ready. And then I think this will all work out pretty nicely. So let me plug that capacitor back in, and the program is back to behaving normally, which is nice. So this has been some pretty fantastic progress. It's really cool to have a Fibonacci series now printed to the LCD instead of looking at register values and trying to figure out what the concrete values are. And even though the display takes quite a few cycles to execute these commands, we do all of this without any knobs in the program to wait for the LCD. Instead, we're using this ready valid handshaking mechanism to have the LCD unit report back to the decoder and the CPU if it's ready to make progress, or when we're reading, if the result is ready or not. And then the decoder can make a decision and basically stall the program counter, halt the program entirely until whatever the resource contention is has cleared up. When we're writing, we're just waiting for the display unit to become idle, and when we're reading, we're waiting for data to come back. And this ready valid handshaking is extremely common in digital hardware design. In modern hardware engineering, you will find that all over the place, and all kinds of communication protocols, but also the individual pieces that make up the complicated CPUs you find today are often based around this ready valid handshaking. And in a sense, it's a little bit of abstraction like you would use in software, but applied to hardware. there's two signals, valid and ready, where two sides of a communication interface can indicate that there's valid data available to process, and then the downstream circuit can report back if it's ready to make progress. And regardless of how we figure out that we have valid data, or regardless of how the downstream unit figures out if it can make progress or not, if it's ready to accept the data, we just have two single wires that act as an abstraction and communication point where we sync the two up. And we can build pretty complicated hardware around that simple, clean interface in the hardware. The one downside right now is that the CPU is idle while it's waiting for the LCD read data to come back. It's not really a big problem in this program, but later on, you can imagine that we'll have other functional unit, not just a display, maybe a multiplier, where we want to have the CPU run ahead and continue with the program and not stall on the multiplier unless it actually needs the result immediately for the next instruction. And there's actually a fairly straightforward way to start doing this kind of out-of-order execution. And what we'll do in one of the next episodes is give the LCD unit the capability to write the result it gets from the display back into the register file independently of the decoder. And this will allow the CPU and the decoder to fire off a LCD instruction that then runs in the LCD. And even if it's a read, the decoder and the CPU can make progress and continue in the program because the decoder will remember which register it needs to write back to. And when it's done, it will just autonomously return the data that it produces back into the register file. And this is going to be pretty interesting because at that point we have the regular part of the CPU, we have the move buffer and the ALU, both of which want to write to the register file. But then we also have the LCD unit, which wants to write back to the register file. So we have two sources of write back data that goes into the register file. And as you can imagine, when the CPU is doing its thing and suddenly the LCD wants to write back to the register file too, there's going to be a resource contention because both want to write. And this will require us to build out a proper write back bus and have proper arbitration where we look at whether the LCD unit or the rest of the CPU want to access the registers, and we make a decision of who goes first. And when we do this for the LCD, it's only going to be a small step to then also do it for a load store unit, a multiplier, a divider, whatever we come up with. This will allow us to separate the CPU pipeline quite substantially, where the program counter keeps track of the location we are in the program, then an instruction is fetched, thrown at the decoder figures out what needs to be done, and then throws that instruction at the rest of the CPU in a kind of fire and forget fashion, and then the different parts of the CPU can just execute their instructions independently and write back results. And all we need to make that work is a centralized registry if you want to remember which registers are currently invalid and have data in flight. And then we can use that information to stall the CPU in the case where we try to execute an instruction that doesn't have a result ready yet. So that's going to be very fancy, and that's going to move us very solidly into the realm of out-of-order execution, or more precisely, out-of-order write back of the results. We'll still execute instructions in order, but we'll go about fixing that soon too. So in the next few episodes, I think we'll look at realizing such a write back bus into the register file to have these units operate independently. And then looking at the assembler a bit, there's a lot of refactoring I think we should do, simplifying the assembler and coming up with better ways to specifying opcodes and maybe documenting a little bit what's going on there. And then one thing I keep noticing is that as I work with this clock generator, because it's a pretty old breadboard and the connections are flimsy, I think this one should go on a PCB pretty soon. So there's a lot of cool work ahead, and we're solidly moving towards out-of-order execution, which is fantastic to see. Thanks a lot for watching. Like and subscribe if you want to see more of this, and see you next time.